This is part 4 for section 5.5, which is exponential and logarithmic models. So we're looking at a bacterial growth type of problem, which would be exponential growth. As you can see here, we've got some variables up in the exponent, so it's exponential growth. It's very similar to the one where we had to find k before for the half-life problem. In that case, finding the half-life value for k was always the same. It was always k equals the natural log of 1/2 divided by the number of years for the half-life. Well, this is similar to that in that we have to find k. K is not going to be given to you, but it's not always going to be the same. It depends on the bacteria that's being grown, that sort of thing. So we have this general formula, but I want to be able to rewrite this formula. I want to know what the k value is. So in a case like this, what they're going to do is they're going to give you some data that lets you find k before you solve the problem. So it says the number n of bacteria in a culture is modeled by this equation, where t is the time in hours, so make sure you make a note of that. The other one was time in years. This is time in hours. But it's going to give us this part right here, where it's some sort of data that has been collected, where they figured out that after 5 hours, there was 300 of this bacteria, where they had started off actually with 100. This number, remember, is an initial amount. So we need to figure out what the k value is for this particular bacteria. So that's the first step. Step 1 is to find k. And you're going to do that by substituting in this value, and the only thing left will be k. So I will get 300 equals 100 e, and then 5 times k will be that exponent. So I'm going to solve for k. Same way we've been doing for every other problem where the variable is up in an exponent. First thing I'm going to do is get this exponential part by itself. So I'm going to divide by 100. So I get 3 equals e to the 5k. Now that that is by itself, I can get this exponent out of the exponent. 5k equals, by doing the log with this base, so the log base e, that's called the natural log, of the number that's on the other side, which is 3. So if I now divide by 5, I get that k is equal to the natural log of 3 divided by 5. Now be careful, that's not the natural log of 3/5. That's the natural log of 3, that's an answer, and then divided by 5. So the second part is going to be that I'm going to rewrite this formula. N equals 100 e, and now k is the natural log of 3 divided by 5, and then times t. So first part is to find k, so you could rewrite your formula for that particular bacteria with its k value. Now that I've done that, I can actually look at what it wants to know. It wants me to estimate the time required for the bacteria to double. Okay? So for it to double, again, I have to know that this 100 represents the initial amount. So for it to double, that means n would have to be 200. So 200 equals 100 e to the natural log of 3 over all divided by 5 times t. So this is similar, this part is kind of similar to the interest problems where we wanted to double our money or quadruple our money. The first thing I'm going to do is divide by this 100, and you'll notice this side becomes 2, which is not a coincidence that we're doubling, and that's a 2. If I was trying to triple it, that would be a 3 there. So then I have e to the natural log of 3 divided by 5 times t. So again, similar scenario that we keep running into. I have a variable up in my exponent. So I'm going to rewrite this as the natural log of 3 over 5 times t. So my exponent is equal to the log with this base, so it's base e, so again, that's natural log, of the number that's on the other side, which is 2. So to solve for t, I just need to get rid of this fraction. And so fraction times a variable, you multiply by its reciprocal. So I can simply multiply this Probably better to put the 5 in front, so 5 times that, that's 5 on top, and the natural log of 3 on bottom. So all of that's gone, so this is what t is equal to. That's an exact value, but of course that exact value doesn't mean anything to us. We need to grab a calculator and get an approximate value, and it comes out to be 3.155 hours. And as I showed you before, it was very important that I pointed out that the time was in hours. So when we solve for time, we know that that is what the hours is. So that's the end of that section.